Uh, Good evening, sir. My name is Yashwardhan, Sant,
My name is Kalash Maheshwari.
and our topic is inter-process communication. So today I'll be discussing the various approaches, challenges, and innovations in inter-process communication or IPC as covered in our research papers. And each of these papers provides a unique perspective on improving and refining IPC mechanisms, particularly in the context of operating systems. The scope of these papers spans different systems, including the Windows OS, OS level virtual machines, and distributed OS designed using CSP notation, which are communicating sequential process. Additionally, they explore interoperability between mobile operating systems, synchronization in microkernels, and also the use of hardware-assisted IPCs. Furthermore, emerging communication methods within virtualized environments are also explained, adding a forward-looking dimension to the discussion. So, first is approaches to process communication. Now, first we have confinement in virtual machines, particularly in Windows OS level VMs, which are virtual machine. This approach restricts IPC to within the virtual machine, which provides enhanced security and isolation. Next is the communicating sequential process or CSP notation. This method structures process communication in both centralized and distributed operating systems using input and output operations, which offers a clear and systematic way to handle the communication. Then there's an interoperability framework for mobile operating systems, which allows communication between different mobile platforms like iOS, Android, and Windows Phone. It automatically adapts communication protocols based on hardware and the data type. Next is synchronization via threads and microkernels, which is also another approach that reduces idle time and improves efficiency in both microkernel and distributed OS environments, primarily through the use of POSIX threads. Next is a more advanced method involves hardware-assisted IPC using a primitive called XPC, which improves IPC performance by reducing the latency and enabling zero secure copy message passing. Now, XPC is a lightweight inter-process communication mechanism, which is used by Apple to create helper tools that perform work for an app. XPC services are launched on demand. They are shut down when idle and restarted if they crash. Next is traditional IPC mechanisms like shared memory, message queues, and semaphores are also compared, each with its own strengths and weaknesses in terms of speed, complexity, and the potential for deadlock. Finally, IPC in virtualized environments is explored through mechanisms like Unix domain sockets, transparent IPC, and Virtuo VSOC, which are particularly effective in container and VM setups, demonstrating the efficiency of different communication techniques in these virtualized environments. Now, what I understood from these papers, from reviewing these papers, I have come to the understanding that IPC is absolutely essential for efficient process management across a wide range of environments from mobile OS to virtual machines and distributed systems. What stands out is the diversity of approaches, which shows that IPC needs to be carefully tailored to the specific architecture of the system. For example, hardware-assisted IPC can be crucial for improving performance, while framework-based IPC is important for ensuring interoperability across platforms. However, each method comes with its own trade-offs, such as balancing latency against complexity or security against performance. I also noticed that as systems evolve, so do the models for IPC. New innovations like the XPC primitives, which are used by the Apple, or CPF cross-process frameworks, are designed to enhance communication efficiency and reduce the chances of errors like deadlocks. So the future of this, uh, looking ahead, the future of IPC appears to be moving towards greater automation, enhanced security, and deeper hardware integration. With innovation like XPC primitive, many of the performance bottlenecks that exist in traditional IPC methods are being addressed. We can also expect to see frameworks that automatically handle compatibility between different OS or virtual environments becoming more widespread, particularly as mobile and cloud-based systems continue to expand. As virtualization continues to evolve, there will be an increasing need for more sophisticated IPC models that not only minimize the performance overhead, but also maximize the isolation and scalability. So the limitations, potential challenges, and needs are while IPC has made significant strides, there are still several limitations and challenges that needs to be addressed. First is the performance overhead remains a great concern. Methods like shared memory or message queues can create bottlenecks, especially when managing large-scale communication or handling multiple processes at once. Security and isolation are also critical challenges, particularly in virtualized environments, ensuring that IPC should remain confined within the between the virtual machines and the host system is an ongoing struggle, which has led to the development of more restricted inter-process communication model. Synchronization issues such as the risk of deadlocks, race conditions, and excessive waiting times continues to be a problem in both traditional and microkernel based systems. Next is when it comes to cross-platform interoperability, ensuring smooth communication across different OS, especially mobile platforms, requires continuous adjustments to the frameworks that handle this process. Finally, there is a growing need for hardware support. Hardware assisted methods like XPC show promise in overcoming latency and performance limitation, but they need to become more widespread and support across a variety of architectures. So the conclusion of this is the evolution of IPC is very crucial for the future of computing across virtual, mobile, and distributed environments. Enhancing the security, performance, and automation will be a central to overcoming current limitations. Kalash?
Now I will be discussing critical aspects of modern computing system. Inter-process communication or IPC is essential for enabling communication and data exchange between different processes in both embedded and distributed systems. As computing systems continue to evolve and become more complex, efficient, IPC mechanisms have become increasingly vital. This is especially true in energy constrained and real time applications such as those found in the Internet of Things IoT and edge computing. The studies I will explore today highlights various IPC technologies and modeling approaches, focusing on their impact on energy consumption and performance in distributed system. We will also look at the growing need for energy efficient and low latency IPC design. The approaches. Energy estimation through AADL modeling. The architecture analysis and design language or AADL is used to create model of IPC mechanism. This modeling approach enables systematic estimation of energy consumption in embedded system. By using AADL, engineers can identify potentially energy bottleneck early in design process, allowing for more efficient design. Remote IPC technology. Several remote IPC technologies are investigated, including remote procedural calls, RPC, message passing interface, MPI, and sockets. Each technology is assessed for its energy efficiency and delay characteristics, helping to determine the most appropriate option for a given application based on its specific needs. Performance evaluation. Multiple studies have focused on evaluating IPC mechanism based on metrics like latency, throughput, and energy consumption. Empirical data gathered from this evaluation provide critical insights that inform design decision and help optimize IPC mechanism for real-world implementation. Energy delay trade-offs. An important area of focus is analyzing the trade-offs between energy consumption and communication delay. The study suggests that optimal IPC choices are often application dependent, meaning each system requires careful consideration of its specific requirements and constraint to make the best choice. Now, future scope. Enhanced energy model. Future work should aim to refine energy models for IPC mechanism by incorporating di- diverse operating condition and varied communication pattern. This model can offer more accurate prediction of energy consumption across different scenarios. Integration with machine learning. There is significant potential for integrating machine learning techniques into IPC analysis. By analyzing historical IPC pattern, machine learning can enhance predictive capability regarding energy consumption, allowing for approach optimization. New IPC mechanism. Exploring innovative IPC technologies that prioritize low latency and energy efficiency will be critical, particularly in meeting the requirement of next generation application in IoT and edge computing, which demand high responsive and minimal energy use. Cross-platform analysis, investigating the performance of IPC mechanism across various platforms such as cloud, edge, and mobile can deepen our understanding of their effectiveness in different environments and guide adaptive system design. Now, limitation, generalizability. Many studies focus on specific IPC mechanism or particular use case, limiting the applicability of finding to a broader range of systems. This narrow focus can hinder our ability to draw universal conclusions that apply to diverse environments. Complex of real world application. World application often exhibit complex communication patterns not fully captured in experimental setups. Simplified models might overlook critical factors that impact IPC performance in practical scenarios. Static models. Some IPC models do not account for dynamic changes in system states or fluctuating workloads. This limitation can significantly impact the accuracy of performance and energy consumption predictions, leading to sub-design decision. Overheading in modeling. The introduction of sophisticated model tools such as AADL can add overhead to design process. While these tools provide valuable insights, their complexity may be less practical for rapid assessment, especially in time-sensitive application. Potential changes. Synchronization issue. Efficiency synchronization among processes is crucial but can lead to increased energy consumption and delays, particularly in shared memory systems. Balancing this synchronization demand with performance needs remains a significant challenge. Scalability. As the number of process and communication complexity increase, maintain efficiency in IPC mechanism become more difficult. Scalability challenges can hinder the implementation of IPC in larger, more complex systems. Network variability. In distributed system, varying network condition can significantly impact IPC performance. These fluctuations make energy consumption estimates challenging and can lead to inconsistent communication experience. Integration of emerging technologies. Integrating new technologies like 5G and IoT with existing IPC mechanism presents challenges in balancing performance and energy efficiency. Addressing these integration issues is essential for advancing IPC technologies. Now needs comprehensive benchmark. There is a pressing needs for standardization benchmark that can effectively evaluate and compare IPC mechanism across different systems and applications. Standardization would facilitate more consistent assessments and enable better informed decision. energy-aware design tools. Development of design tools that facilitates energy-aware decision-making during the early stages of system design is essential. These tools should be allow designers to simulate and estimate energy consumption with ease, leading to more energy efficient system. Interdiscipline, interdisciplinary collaboration. Collaboration between computer scientists, hardware engineering, and domain expert is vital for developing IPC mechanisms that meet performance and energy demand. Interdisciplinary efforts can foster innovative solutions to IPC challenges. User-centric models. Future researchers should focus on user-centric models that assess the impact of IPC mechanism on user experience, particularly in real-time system. Understanding user needs can guide the development of more effective IPC strategies. Conclusion. In conclusion, the studies we have examined underscore the critical importance of IPC in contemporary computing system, particularly in terms of energy efficiency and performance to meet the evolving demands of distributed and embedded system. Ongoing research must focus on deploying more sophisticated models and tools that facilitates informed decision making in IPC mechanism section. Addressing the identified limitations and challenges will require enhanced collaboration and innovating approaches. Ultimately, the future of IPC will hinge on balancing performance needs with energy constraints, ensuring system can adapt to complex landscape of modern computing. Thank you.
Thank you.